In this video, we're going to look at path difference. Path difference is the difference in the total distance of the path traveled by the waves before they meet. So one example here, let's say we have source A and B generating the wave that travel to meet at point C. Okay, so we can see that AC, it took 2 wavelengths to reach C, and BC also is 2 wavelengths. Okay, means that the difference is 2 wavelength minus 2 wavelength, that's 0. If let's say B now move 1 wavelength further behind, so B is here and A is here, C is still here, then we can start counting again. This one is 3 wavelength and this is 2 wavelength. So in this case, the path difference is 3 lambda minus 2 lambda, that's the 1 lambda. So just now is 2 lambda minus 2 lambda, that is 0. So now let's look at the similarity of the two of them at point C. So if let's say we put a readout, okay, so for example there's a device that can let us translate its displacement into the reading on a CRO screen, okay, just like the animation that we did that day. Then we can plot it on a graph to become like this. So let's say this is from A and this is from B at point C. So both of them are at point C. Okay, so we put the meter here. Then we look at how both of them oscillate at that point, and it is going to be in phase. So we'll see both of them up and down at the same point there. Okay, so then we use the principle of superposition to reason out what is their resultant displacement there, because they are meeting at that point, right? So they are going to give you a resultant wave. That means displacement will change. So how it change, of course, according to the principle of superposition is it will add up and then become this. So this is basically the resultant, and we can see that it become bigger at any point, okay, except the 0 huh? Okay, then we look at the second case here where B have moved backwards. So that's path difference of lambda, and basically there's no difference in its resultant. Okay, basically there's no difference in the resultant. So both of this case, it causes a constructive interference. It's going to build up the resultant displacement. So now if I ask you if the path difference is 2 lambda, 3 lambda, 4 lambda, 5 lambda, so what will you say? Are they going to show you the same resultant displacement as in the first case, or they are going to be different? Answer, of course, is the same, because no matter what is the number of lambda, at the end when they arrive here at C and you place a 2 meter there, they are going to just oscillate in phase. Okay, so constructive interference when the two waves meet like that is going to be obey if the path difference, okay, there will be constructive interference if the two sources of the wave emitting a wave that arrived there with a path difference of n lambda. So n being 0, 1, 2, 3, and so on. Okay, as long as it's an integer, then we will get a constructive interference. Okay, no matter how many waves that meet there. All right, let's move on to the second part of it, that is the destructive interference. Destructive interference, of course, is where the two waves, they cancel off each other. Okay, and then it will give you a 0 if the two of them having the same amplitude. Okay, so in this case here, let's say I have the A and D. Don't use B again. Huh? So again, they meet at point C. Okay, so they are going to meet at point C. All right, then we start to count the sorry, let me let me erase some of the things first. A, D, and C. Okay, and we start to count again. This is 2 lambda, and then this is 2.5 lambda. So this is a half lambda here. Okay, D has a difference of has an extra distance of half a lambda. So path difference of these two is 2.5 minus 2 lambda, which will give us 0.5 lambda. 0.5 lambda, if you again we put the meter here and then we read out on the CRO, we can see that there are 2 points that move up and down like this. Okay, so they are half a cycle and chasing each other by a phase difference of pi radian. Okay, so putting on the graph will be like this. So this is from A and this is from D at point C, at C. Okay, so they are going to give you 2 waves that are pi radian in their phase difference. So if we pick any pair of that value at any time, so this is time, okay, this is time here, then it will actually cancel off at any point or for any pair of the displacement at different time. So all will give us 0 there. So that means at the end there, at point C, you will see no waves at all. Given that the 2 amplitude are equal, so you will see no wave at all. That is the destructive interference. So what if now I change to I move the D. I move D by a wavelength. Okay, I move D by a wavelength, 1 wavelength. Then the path difference will now become 1.5 wavelength. If I move another, then it will become 2.5 wavelength. So as long as I can see the 0.5 wavelength of the path difference here, it is going to give me a destructive interference. Okay, you must get the 0.5. So means that the criteria for the destructive interference when waves meet, right, it is n plus half lambda, where the n start from 0, 1, 2, same like the constructive interference just now, but this one has an n plus half lambda. Okay, so these 2 criteria you got to remember. Yeah, because later when we talk about the next thing, we will need this one also, and in the exam, if you can remember this, that will come very handy. Okay, let's move on. 2 source interference pattern. Okay, so you actually have this this piece of the worksheet at the end of your example and exercise worksheet. At the end there, I give you this diagram, but you can see that I blurred it out a bit. Okay, because I want you to draw on it. Okay, I want you to trace those waves. So what you can do, what you should do is, so first of all, you look at the 2 waves from A and B that arrive at C. Okay, we start off with C first. So these 2, A and B, there are 2 sources that is emitting the wave. So I want you to trace on the paper by doing this. Sorry, you can't see the ink, so I change to another color first. So I want you to trace that. Okay, you just trace on your paper. Okay, so same thing here, you trace on it. Okay, how do you want to do it? It's up to you. You want to use a color pencil, so can. You want to use a pencil, so can. So after you trace that, right, you count the number of waves. Okay, we do one by one. Don't just trace everything first. So after we trace the A and B that is reaching the C, you can pause the video at any time that you want so that you can finish doing. I'm just going to continue talking. So after that, you count. Okay, so once you finish tracing it, then we count the wavelength. So we have 1 wavelength, 2 wavelength, 3 wavelength, and 4 wavelength. So 4 lambda, that's the distance from A to C. And then we count B and C. So 1, 2, and then we have the 3, and then 4. Also 4 wavelength. Okay, you can count on your own paper. It's the same diagram. So basically, they have 0 path difference because 4 lambda minus 4 lambda, right? So 0 path difference is going to be a constructive interference. Okay. okay, as we already learned just now that I say you must use that, you can use that here. Then we look at the case of D again. I mean, we look at the case of D now, where they meet at D. So again, you trace the AD and the BD here, and after that, you count. Okay, let's count together. 1 and 2 and 3 and 4 and 5. 1, 2, 3, 4, 5. So there are 5 lambda. If we count for B, that will be 1, 2, 3, 4, 5, 6. That's 6 lambda. Okay, so BD is 6 lambda and AD is 5 lambda. So in total, I mean the difference is a wavelength. Okay, so this difference is a wavelength. So a wavelength means it satisfies the condition for the constructive interference, and therefore it will add up here. It will build up the displacement here. And we look at the last case, E. Okay, E, you trace, then we count now. So we have 1, 2 is a bit messy, sorry, 3, 4, and 5. 5 wavelength from A, and then for B is 1, 2, 3, 4 and a half. So 5 minus 4 and a half, we get half a wavelength. That's why it's written here. Path difference is half a wavelength, and that's the criteria for the destructive interference. Therefore, they will destroy each other, and we get a 0 here. Okay, so imagine like this is a water wave. Then we will see that at C and D is like a higher wave, and then at E is like no water waves. Okay, if let's say there's light, then C and D will see bright light. At E, then we'll see no light. Okay, so next question, the next thing that I want you to think about is, at this point here, somewhere in between the C and D, what do you think is the path difference? C is 0, D is lambda, 1 wavelength. In between here, logically, it should be increasing from 0 to wavelength, right? So that means somewhere in the middle here, it must be a path difference of half a wavelength. Okay, hopefully it makes sense to you. So half a wavelength, then this point here is destructive interference. So we have constructive interference followed by destructive interference, followed by constructive interference, followed by destructive interference as you go higher up. Okay, so based on the concept of path difference, now we know that if we have two sources of waves that interfere in such a way, they are going to produce a constructive and destructive region. Okay, regions. Okay, constructive and destructive regions, and this is what we call earlier the interference pattern. So they have a region of constructive at C, region of destructive at somewhere in between C and D, and then D, and then we have destructive, constructive, destructive, constructive. As we go on, we also have the pattern, the similar pattern as we go along the line of CDE there. Okay, all the way down and all the way up. Okay, because we know that the path difference is going to increase by half. So 1 wavelength, 1.5, 2 wavelength, 2.5 wavelength, 3 wavelengths of the path difference. Okay, so that will give you a whole band of the bright and dark fringes, or the pattern as you use light to interfere. Okay, that's what we are going to look at in the next video. Yeah.